Welcome, everybody. We're just going to wait like another minute or two as people populate. All right, everybody, welcome. Um, First, welcome to a usability and system evaluation TG webinar. We're going to first do some housekeeping. If you have any questions, feel free to put them in the chat box. We're going to keep everybody muted and camera off for this presentation, but we're going to be monitoring the chat to answering the questions that you have. Because this is going to be recorded, we're going to have a Q&A also at the end. Please also, if you would, participate in the post-event survey that's going to be sent out. And that's another opportunity for you to touch base with us, as we're going to be able to read those responses from you as well. So today I'm super excited to talk about or have a speaker talk about the NASA TLX. I met Skye at Aspire, and she was sharing her findings. And then I followed up with her with lots of other questions, and I found that she was doing all this other work about the design of this instrument. And we talked about how it's traditionally used and how people really use it and the impact it's having on outcomes. And it was so neat. So I reached out later and I said, would you be willing to do a webinar? And she said yes. So I'm really excited to have her come and share some of her recent findings with you today. So Skye Taylor is a PhD candidate at the University of Virginia, and she's a presidential fellow in the ISE area. Her research focuses on designing and evaluating subjective measurement tools. And so it's just great to have her sharing with the use group today and people that are interested in this stuff. So I'm going to go ahead and turn it over.
Thanks, Jeremiah. Yes. Hi, everyone. My name is Skye Taylor. And what I'm going to be presenting today is what I've been spending my dissertation working on. I actually have my defense scheduled in a week and a half, so I'm super excited to have this opportunity to present it to you all first and answer any questions you might have. The NASA TLX is something that has been a tool that I have used since I started human factors research. And since I first started using it, I've always had some questions about it and noticed some usability problems that it's had. So without further ado, I'll just go ahead and jump into my presentation. So before we jump into the NASA TLX, I think it's important to discuss mental workload, which is the construct that is measured by the TLX. This is a crucial construct within human factors for engineering safe engineering designs and human system interactions. So mental workload is this latent psychological construct which has been defined in many ways throughout the literature, but today we'll be going based off of the definition that's used for the way that the NASA TLX aims to measure mental workload, which is the costs incurred by the operator of a task to achieve a certain level of performance. So this construct is of particular interest, especially in human factors research, because it is highly correlated with human performance. such that when operators or users or participants experience mental workload that is too high or low, their actual performance on the task degrades, and the likelihood of errors, mistakes, or lapses increases significantly. Therefore, it is critical that the tools we use to measure this construct are reliable and accurate, because they inform the design of critical engineering systems, such as aviation, which is pictured here, where people are evaluating users' workload in a aviation tracking monitoring task. It's also used to evaluate different systems in manufacturing and healthcare and pretty much anywhere where humans do work. So the NASA TLX is the gold standard for mental workload measurement. It was developed by NASA by Sandra Hart and Staveland, and the development resulted in the famous 1988 paper, which has been cited over 20,000 times. It says here, actually, that number is out of date. In the past, year or so, that has jumped up to 21,000. So there's an explosive use of NASA TLX throughout the literature. So what is the NASA TLX and how does it measure workload? It is a subjective multi-dimensional rating scale, and it aims to estimate the workload experience during different tasks along 6 subdimensions of workload, including mental demand, physical demand, temporal demand, performance, frustration, and effort. So traditionally, when using the NASA TLX, an overall workload score is determined based on ratings provided on the scales shown in the last slide, along with pairwise comparisons of those ratings. So in the paper pencil package that was published by NASA, they provide these pairwise comparisons, and participants are asked to select for the task that they are presented with which of the dimensions of workload contribute more to the workload experience during that task. And they're asked to provide these selections for all of the 15 comparisons between the unique dimensions. And then the weight for that dimension when calculating overall workload is determined based on the number of times each dimension is selected out of the total 15 comparisons. And then this is calculated into an overall workload score by multiplying the weights by the ratings that are provided on the scales. So these are the original scales from the instruction manual, and participants are asked to place a mark, typically an X, on the line that best represents the workload that they experienced. So this 21 ticks on these lines, on these scales, and then the distance of their marking from the left side of the scale up to the right side of the scale is scaled from 0 to 100 based on the distance from the left end. And then the overall workload score is a weighted average of these ratings. However, what I showed previously in the original version is a bit different than what we see in other official documentation of the NASA TLX. So on the NASA TLX website, there is a link to 2 versions of the TLX. There's the original instruction manual, as I've mentioned previously, but there's also another version that I've actually recently found. I couldn't figure out where they got this version from. It looks like it's taken out of a book somewhere, because it's called Figure 8.6. But it is unclear exactly where this version was taken from, but it can be found on the NASA TLX website. And if you can't tell already, there are a couple different design elements between these versions. So first of all, the tick patterns in the original version are alternating in size, with one tick in the middle that is longer than the other long ticks, whereas the modified version available on their website has static tick marks besides a longer midpoint. They also use different anchor labels. So the original version, the scales are ranging from low to high. The performance dimension actually has different anchor labels, but I will get into that later. And then in the modified version, the scales range from very low to very high. And then finally, they have different descriptions or prompts for what these subscales mean. So they have the title as mental demand, and in the modified version, they ask a short question saying how mentally demanding was the task. But in the original version, in the manual, the descriptions of the scales are actually presented separately from the scales themselves, and they're much longer and more descriptive. So, for example, here you see the mental demand description is how much mental and perceptual activity was required, thinking, deciding, calculating, remembering, etc. And then was the task easy or demanding, simple or complex, exacting or forgiving? Also on their website, you will find a link to the NASA TLX app, which displays additional elemental design differences. So it has the same tick mark patterns from the modified version, but it uses the anchor labels from the original manual version. So these are some of the differences in the scale designs that we see in the official materials, but in the literature, there are a lot more variations of how you see NASA TLX produced and used to collect workload ratings. So practitioners can use different scale orientations, different feedback indicators, so how people can see what response they've selected. There's slider scales, some use numeration and some don't. Some are continuous, some use dichotomous radio buttons. And the variations go on and on. As someone who has participated in a lot of human subjects research, as well as conducted it, I can say that I've seen a different NASA TLX scale design in basically every study that I've participated in. And that was kind of the motivation behind this research, because these design differences might seem benign and non-trivial, but different scale designs based on psychometric research can have serious implications for interpreting participants' mental workload ratings and all of the design decisions that follow those analyses. So some studies have shown that visual scale designs can impact response behaviors and data distributions. They can introduce noise and ambiguity to the resulting data. They can bias ratings based on initial handle locations when you're using a slider or a knob. And especially when you're using continuous data versus dichotomous radio buttons, like what you see on the bottom here, that can alter the fidelity of the data that you're collecting. So having all of these different variations available and used throughout the research can make our understanding of mental workload measurement hard to compare between studies, and we can see different patterns and properties in mental workload data when we're using all of these different tools to assess it. So another issue with the NASA TLX in its official documented format is that in the paper pencil package, when you are using a pencil or a pen to mark your rating, the developers actually mention a common use problem, which is that participants sometimes respond on the tick marks on the scale, and sometimes they respond on intervals in between the tick marks on the scale. And in order to mitigate this issue when it comes to actually evaluating the data that is provided. The manual instructs researchers to round the ratings up to the nearest tick on the right. But there are some problems with this. Obviously, this is important when you're in a paper and pencil format to make the facilitation of data collection and evaluation easier. But the NASA TLX is typically administered electronically or digitally now. So it's not necessarily as important that rounding is used. But this essentially means that we're rounding ratings up to the nearest 5, which doesn't seem like a huge change or transformation of these data points. However, for example, let's say you were rating your mental demand on a task and you placed your tick mark on the bottom scale I'm showing here, just to the left of the midpoint of the scale, because you were trying to say, I feel slightly lower mental demand than perfectly neutral between low and high. But these two ratings, if I marked on the midpoint tick or just to the left of it, that now has the same meaning when you apply the rounding transformation. Another common use issue that is discussed in the official and original NASA TLX instruction manual is that the performance scale can be confusing for some users. And that's because compared to the other 5 TLX dimensions, the performance scale is rated from good on the left to poor on the right, unlike low and high. And this was done because having a poor perception of one's performance contributes highly to the overall workload. And this scale orientation allows all of the 6 NASA TLX dimensions to have the same increasing relationship. As workload increases, all of the scale ratings should increase. But changing these anchor labels can be kind of confusing because having poor performance might be conflated with having low performance, and good with high, vice versa. And this has just been shown to be confusing to people. And we also are pretty confident that people don't notice that the scale is oriented differently. And according to the psychometrics community, reversed items often result in misresponse, especially when conducting multi-item scales. So all of these problems that I've mentioned have been speculated about the TLX, even by the original developers, but they have not been empirically evaluated before this work. So our goals of the research I'm presenting today was to first assess the impact of response scale format and rounding. So those overall response formats, like the variations I showed previously, we wanted to see how using different response input methods can impact rating behaviors, as well as experimental conclusions. And we also wanted to compare rounded ratings to raw ratings on a continuous scale. We expected that we would find some differences there, in which case we thought that it would be important to also evaluate the effects of the more subtle design differences that are seen in the official NASA TLX versions. And in our final aim for this research, we wanted to investigate the reversed TLX performance scale to evaluate how it contributes to misresponse in NASA TLX ratings. So the first research effort I'm going to discuss deals with our aim 1, looking at the different response scale formats and rounding. So this research was actually a secondary analysis. It kind of served as a proof of concept for the remainder of the work we're going to discuss today. But we took data from a study by my advisor that he conducted at the University of Buffalo before we started our research work together. And in this research, participants completed tasks in a UAS, or an unmanned aerial vehicle simulation or system simulation. And they reported their perceived mental workload on NASA TLX ratings. But instead of using the standard scales, 3 different response formats were used. So a rotary knob option was used as one of the response inputs. We also used a slider scale, and another version of response input we use, similar to administering the NASA TLX verbally, is just we asked participants to enter a number from 0 to 100 relating to their rating. And all of these had the same fidelity of responses. I believe it was up to the 10th decimal place, not the 10th decimal place, but a 10th of a integer. So our findings indicated that providing NASA TLX ratings on different response formats actually resulted in significantly different response distributions. So for all of the TLX dimensions besides effort, we did analyze the dimensions separately. We found that the ratings were significantly different between the response format groups. And we found that the knob format tended to result in higher rating distributions than the slider, followed by the ask format. And then after we conducted this analysis, we took all of our data observations and we applied the rounding convention. So everything was rounded up to the nearest 5, as it would be if you were measuring on the paper pencil version and rounding up to the nearest right tick. And what we found here was response format still had an effect here. And actually, when performing the rounding operation, more of these comparisons became significant. And what we found was that in the ask format, participants seemed more inclined to answer in round numbers, such as like multiples of 5 and 10. And so when you apply the rounding convention, the ratings provided in the ask or open response format were not changing very much, but compared to the other response formats, those increased significantly. And so that's why we believe the number of significant comparisons here increased. Another thing we wanted to look at for this study was, okay, we see that the response formats do result in different rating distributions. We see that rounding results in different data distributions. But if we were to be using the NASA TLX in a standard experiment where we wanted to test different system parameters, would the conclusions from the experimental analyses be different depending on what response format or rounding that we used? So in the initial study, there were task manipulations of different difficulty levels, including in the UAS task, how big the radius around the UAS the users could see, how fast the simulation played, the noise of their cursor. So their cursor like jittered around a little bit as they were having to respond in this task environment. And then also in some conditions, they were able to see the flight path of the UAS, and in other conditions, they were not. So we compared the ratings between these different variable groups to analyze pseudo hypotheses about NASA TLX ratings to see if the statistical conclusions would be different depending on what response format was used. We also did the same analyses on the rounded ratings, and we found that the order or comparison between the different variable levels, for example, small versus medium versus large radius, the magnitude of those values stayed the same in terms of like small radius was resulted in consistently lower ratings than medium radius, than large, etc. But which pairwise comparisons of those three groups manifested significance were different depending on which response format was used. So essentially, experimental conclusions can be biased depending on how you're eliciting NASA TLX ratings. We also looked at the rounded ratings, and our results were replicated by the rounded ratings. So using rounded ratings instead of raw ratings did not result in different significant comparisons. So that means that studies that use rounded ratings versus studies that use unrounded ratings will not have different experimental outcomes. So in summary, for this research push, we found that response format did affect rating distribution significantly, and knob modalities tended to result in greater ratings than a continuous slider, and the slider ratings resulted in greater rating distributions than an open response or ask format. We also found that rounding does significantly alter the ratings or responses produced by participants, and that the disparities between response formats seem to be increased when the rating convention is applied. And as I mentioned, we saw different significant comparisons depending on which response format was used to elicit the TLX ratings. So the key takeaway from this research is that we were able to determine that response format and design as a whole does have impact on NASA TLX ratings, which motivates our next aim, looking at the more subtle characteristics of the official NASA TLX versions. And if you are interested in looking at this data set, it is publicly available online, and I'm happy to share that with you all after the presentation. All right, so in the next goal, as I mentioned, we evaluate the difference of the different design elements seen in the official NASA TLX documentation. This was a human subject study that I designed and ran, and we had participants complete tasks in the multi-attribute task battery to serve as the stimuli for NASA TLX ratings. And they evaluated the NASA TLX on 8 different design variations, including the elemental differences of the 2 versions found on NASA's website. So we measured participants' NASA TLX dimensions as well as their performance on the MAP-B tasks. And these were the 8 different design variations that were used. So this is the full factorial set of differences observed in the original version or the official versions. So we have alternating versus static tick patterns. We have prefix versus original anchor labels, so using low to high versus very low to very high. And in the performance dimension, the original version goes from good to poor, and the modified version ranges from perfect to failure. So that's what anchor labels were used when this was the performance dimension. And then we also looked at using the long prompts from the manual versus the short prompts seen in the modified version. So when comparing the overall designs, so the ones that you see here, we did find that ratings were significantly different on two of the TLX dimensions. So when evaluating participants' temporal demand ratings, we found that the difference between designs 4 and 5 was significant. Design 5 resulted in greater ratings than design 4. And in the performance dimension, we also saw a significant difference between design 2 and design 8. Sorry, design 2 and design 8, as well as design 2 and design 7. So the other NASA TLX dimensions, we did not find significant differences between the overall designs. When looking at the specific elements that were different, so just looking at anchor label differences versus tick type differences, we also had some significant findings. So first, in mental demand ratings, we found that alternating ticks resulted in significantly greater ratings than the static tick condition. And on the performance dimension only, when we used the original manual's good, poor anchor labels, those ratings were significantly lower than when we used the perfect failure anchor labels. So all of that tells us that there are differences when using different design elements, but it doesn't really provide us any information about which design is better for use. And this is limited to the task environment that we were looking at. But we decided to attempt to answer this question by performing canonical correlation analysis. So we looked at the ratings produced by each of the designs, and look at their correlation with the objective performance in the MAP-B task. And in doing this, we found that design 7, which is a combination of alternating tick patterns, the original anchor labels from the manual, and short prompts, had the best overall and consistent correlation with objective performance. So this model was significant, and it had a relatively high maximum correlation. And it was the only model that had multiple significant canonical variates. So it also had the highest overall redundancy, which is essentially the amount of variance described in the ratings by the objective performance measures and vice versa. So what we took away from this research, specifically anchor labels, can significantly impact TLX performance ratings, while using alternating tick patterns can increase temporal demand compared to static tick patterns. And the use of different prompts, so the long versus short prompts, had no impact. I also wanted to mention that the finding we saw in anchor labels was relatively confined to the performance dimension, whereas we only found one significant difference in tick patterns, but across all of the dimensions, the alternating tick pattern scales had higher ratings than the static scales. So overall, the combination of alternating tick sizes using the low-high anchor labels and shorter prompts had the greatest correlation with objective performance measures. And so that is the design that we recommend using until we are able to evaluate this in other task applications. It is also the design that we use in our final study when we're evaluating performance. An interesting finding from this study, even though we weren't looking at the reversal of the performance scale, was that 3 participants throughout the study mentioned at some point in time that they did not notice that the performance scale was different from the other 5 scales until partway through the study. So I think some of these were in the 3rd or 4th trial, but others didn't notice until the very end. And we didn't ask people if they noticed this. This was just voluntary feedback that they provided during the study. So the key takeaways from this push are that we identified that the design differences present in the official NASA TLX documentation can impact results, and the combination of design elements seen in our Design 7 is showing the best convergent validity with objective performance measures. So in the 3rd and final push, we aim to evaluate how the reversal of the NASA TLX performance scale contributes to misresponse. And we used the same experimental setup as the previous study for this evaluation, but instead of looking at the 8 different design variations, we had a between subjects design, and we looked at the different performance scale anchor configurations. So the reverse configuration shown on the top here is what the official NASA TLX version looks like. And then we looked at an option where we use the same anchor labels, good and poor, but we flip the orientation of it so that way it is not reversed compared to the other 5 scales. And then we also used a consistent anchor label configuration, which had the same anchor labels low and high for all 6 dimensions. So all of the other 5 NASA TLX dimensions were the same, but the performance scale was different between groups. And then this was again in the MAP-B task environment. So we measured task performance. We evaluated the TLX dimension ratings with a special focus on the performance ratings, but we also evaluated the other 5 dimensions. We also measured the time it took participants to respond to the performance scale in an attempt to understand if it took more time to understand the scale. And we asked a question at the end of the survey, or at the end of the study, which I will show later, to determine whether participants comprehended the performance scale or not. So we did not find any significant differences between the ratings provided on the performance scale, depending on which configuration of the anchor labels we used. But we wanted to look into this a little bit deeper. And so we evaluated the density plots of the performance ratings. And as you can see here, there's a clear distinction between the patterns you see when the scales are reversed versus unreversed, and when we use anchor labels that are consistent versus inconsistent. So having a more normal curve, as you see here for the consistent configuration group, indicates better inter and intra-rater reliability compared to the reversed curve, because this means that the probability of someone rating at the low end of the scale is about the same as the probability of someone rating at the high end of the scale. We also used linear mixed effects models to determine which scale group was better fit to objective performance rating or objective performance in the MAP-B task. So we fit 3 linear models, one for each configuration group. All of the models converged and had pretty high inter-rater or between subject variability, but the variability was much higher in the reverse condition compared to the unreversed and consistent conditions. And the model fit for the reversed configuration group was significantly greater, meaning that these measures were greater, indicating a poor model fit than the consistent and unreversed groups. The unreversed group, so using anchors ranging from poor to good, resulted in the best model fit evaluations, indicating that this version has the best convergent validity. There was a significant difference between the response time to respond to the performance scale. So when using the reversed condition, the participants took significantly longer to provide their ratings than when using the consistent anchor labels or low-high anchor labels, which is interesting because, as I'll discuss later, the comprehension in the reverse group was much lower. So we were thinking if people took longer to respond, it meant that they noticed the performance scale was different and it took them a long time to figure out how to respond to it. But actually, a lot of people didn't notice that the reverse scale was different. So I think that if they had noticed, this result would be even greater than what we're observing here. So like I said, at the end of the study, we asked this comprehension question. So regardless of what configuration of the performance scale participants saw, we asked them to evaluate these pseudo ratings and interpret what these ratings mean based on what they saw in the performance scale as they were providing their ratings. So if they were in the reversed group, then the answer to the first question here would be that the participant felt successful in the task accomplishment because their scale ranged from good on the left to poor on the right. But what we found was that in the reverse configuration group, their comprehension scores were significantly lower than the consistent group. I think it was only 50% of participants in the reverse configuration group answered both of the comprehension questions correctly, as opposed to the consistent group, only one participant answered one of the questions wrong. So in summarizing these findings, response time significantly increased in a reverse scale. The reverse scale was more difficult for people to comprehend. And during debriefing of the study, several participants claimed that they didn't notice that the performance scale was reversed. So the key takeaways here are that the reverse scale causes confusion, decreases comprehension, and adds time. And we see that the consistent configuration using low to high anchor labels has the best comprehension and a relatively good model fit with objective measures of performance. So that is our recommendation moving forward, is to not use a reverse performance scale. To summarize the recommendations for using NASA TLX, first, we recommend not recreating custom NASA TLX rating scales, especially when their physics and larger general formatting are different between. It's best that we establish a standard scale and method for the NASA TLX ratings. We also recommend analyzing raw ratings rather than rounded responses, even though we didn't see an effect on experimental conclusions. This still increases the ratings for NASA TLX scale responses, and it adds more noise and ambiguity to the responses that we just don't need to incorporate. And we also recommend using low to high anchor labels for all of the 6 dimensions, including performance. However, we do want to mention that when you do this, this means that the direction and relationship with the other 5 dimensions is inverted. So it's best to invert these ratings by subtracting them from 100 before you continue to evaluate the workload as a whole for your studies. Jeremiah, I want to make sure we have enough time for questions so I can maybe save the future work in case we have time afterwards, or
Yeah, I think that's great. So, do you, there's a one really long question in the Q&A. Are you seeing that?
yeah, let me open it up really quick.
Okay.
Yeah. Okay, Robert is asking, does the rating formatting issue matter most if you are comparing between formats? Those are the data you have presented so far. In other words, it would seem that the comparison of averages differing between measurement types shows that there are differences between them, but you wouldn't typically compare them in the real. Yes, so you would not be comparing these in the real world. Thank you for bringing up that point. I think the impact here is showing that the comparability of NASA TLX results between different studies that use different response formats are different. Let me finish reading your question so I make sure I address it all. Versus, I think you also show different input formats that induce different variations. For example, more variation when using a knob versus a slider versus the other responses. This would be more important to show since these could hide a meaningful difference when compared within the same format of response as you would in the real world. I'm not sure if I understand the last part of the question. Do you have some insights to that, Jeremiah?
Yeah, I was kind of when I first read it quickly, and that's why I was like, maybe have you have a look at it. So I'm not just totally abstracting this, but when
Sure.
you look at manipulating these things, which I think is super cool because we're just doing it right now, right? And we do it in different ways. We think,
Hmm.
oh, this probably doesn't matter, but doesn't matter. And so one thing to look at is, I think what was presented just right off the top is, what's the difference between these different types of representations, right, on the data? Did you look at within each type in terms of what is the impact if you're just doing the knob versus, just within there in terms of differences like that? Do you see, in terms of the scale between each of those and then you go within?
Do you mean comparing different dimensions on the same response format?
Yes.
Yeah, so we did not look at that specifically. I think when you are consistent and you're doing NASA TLX evaluation, you're usually not comparing if performance is significantly greater than mental demand. Maybe if you're using it more diagnostically, but our assumption here was that you look at the full picture of these 6 different dimensions to understand how workload is affected overall.
Right.
Um, you can definitely use comparisons between to be more diagnostic. I see that Robert asked another question. If you have 2 measures that differ in variance, because sorry, I'm just trying to read Robert's question. So Robert's asking, considering statistically, if you have 2 measures that differ in variance, so a knob maybe has different variance than a slider, not because of the construct itself, so the dimension ratings, I presume that means then the likelihood that comparison between results in significant differences, knob versus knob with higher variation because of knob rating. It's okay, Robert. So I would be happy to talk about this more offline too, but I think to answer your question, are you asking um, depending on the design of a knob itself and the fidelity of that knob or how a knob is designed, um, that might also cause differences? Is that how what you're taking away from this, Jeremiah?
Yeah, I think we might chat more about it offline. Because
Yeah.
I'm thinking like things are popping up in my mind about, how, you could like with the map B, for example, you could start like varying the degree of difficulty and then looking at
Yeah.
those differences within each type of manipulation that you have. Because I think you're focusing more on
Yeah.
which
So
makes sense,
I,
like absolute values, right? Because like an 80 means something, right? In the general context. So how well can we represent an 80 across these different ways of different ways of representing, right? Am I kind of getting at what you're thinking? And then some people might be looking at it rather than an absolute value, like what's the amount of change that we would observe, right? So if even if it's off, is the difference score indicating that there's greater or lower load, right? And I think maybe those
Mhm.
are two different things. So how robust is it? Maybe to differences, it's
Certainly.
pretty robust. But if we want to try to get an absolute thing that we can all share, have consistency in the measures, then it's sensitive to some of this stuff. I'm not sure if that's
Yes.
exactly what he's getting at, but we can always chat offline. But if anybody else has any questions, throw them in there. I know that we gave Robert's getting a lot of attention, but that's the only question that we have right now.
Yeah.
So yeah.
And I guess while we're waiting for that, I did want to mention to you all and Robert that the first push of this work, AIM 1, where we were looking at the knob and the slider and the open response format, that was a secondary analysis. So we were lucky enough to have data available to look at that, which is why we chose that design in the way we did, because it allowed us to see if if it was even worth it to dive deeper into this and look at the differences that we see in the official NASA TLX documentation. So I think if I were to have run that study, I'd be doing it a little bit differently. I probably wouldn't use a knob, for example, because I don't think I've seen anyone use a knob to collect NASA TLX ratings. Like there are some very large differences, but a knob is quite out there. That study was initially designed to test the level of measurement of the different NASA TLX dimensions, which is why they had three different response formats. But it did serve as a good proof of concept that these differences do have effects. And now let's dive deeper and look into the design differences we see in the official NASA TLX documentation. Mm-hmm.
Okay, awesome. Well, I appreciate it, Sky. I think that we've got a lot to consider going forward, and I look forward to as you follow up on this and think about where we should go and so on. So
Yeah.
I always make a
Thank you.
recommendation to everybody, which is whatever you end up doing, make a template, make it so that we can all adopt it really easily. And I think that that's
Mhm.
something that's my HCI background, right? But anytime we have something we can just grab a hold of, oh, there's some future work. Then I think it just everything's simpler. We don't have to think about it. But yeah, if you wanted to
Yeah.
share, we have a few more minutes. If you wanted to go over some future work.
Sure. Yeah, I think adding on to what you just said, first I wanted to say thank you very much, Robert, for answering, for asking your questions. I'd love to chat more with you about it later. But yeah, so I agree with you, Jeremiah. I think the reason that so many different versions are out there is because there's no great usable standard template. They have the NASA TLX app, but that's difficult to integrate with other study questionnaires that you might be asking. And it also automatically applies the rounding convention, and there's no easy way to get around that. So that's a whole other thing to tackle, which is one of my recommendations in future work is to evaluate the differences in the app specifically. But one of our future work goals moving forward is we want to take what we designed to administer these studies and take our recommended design guidelines and create usable tools that allow people to integrate our design of the NASA TLX into their study configuration, as well as update and improve the instructional materials. The manual that is online is from 1986, and it is pretty thorough, but for example, the weighted NASA TLX workload calculation that we see there is not typically the way that people analyze TLX data anymore. A lot of people use the raw approach, and then my advisor personally recommends not calculating an overall workload score, period. We think that there are some issues with the level of measurement of NASA TLX ratings and that it's best to evaluate them as separate dimensions. So we are hoping in the next year or so to put together a very comprehensive new instruction manual, and also getting in touch with NASA about hopefully promoting these new materials for us, because I think people, when they look up NASA TLX, they're going to want to go to the website and use what is on the website. They're not going to say, oh, the NASA TLX, some girl from the University of Virginia has this website, I'll use that. So we're hoping that we can get in contact with them and get them on board and do more work with them to make sure that these findings are robust across different task domains and applications.
All right, awesome. You're reading my mind. So I'd like to thank Sky for presenting today. Please, if you could fill out the survey when you get that here pretty soon. We'd appreciate your feedback. And this is recorded, so if you know somebody that wanted to come but they were in a meeting or they had work stuff, they can watch it later. So, all right, well, thank you and have a good rest of your day.
Thank you, everyone, for coming.